Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to talk to you guys a little bit about binomial radical expressions. And to get started in this topic, we need to talk a little bit about how we add and subtract radical expressions together. So we'll do a little bit of review with that. And then I want to look at how we multiply radical binomials. One of the really useful applications of multiplying radical binomials is when we multiply radical binomials with their conjugates. And lastly, we will look at the final scale where we will look at how we rationalize binomials using radical denominators. So that is the direction that we're going to go with this video. So with that said, I want to talk a little bit about some basic rules of adding and subtracting radical expressions. And the first thing I want to talk about here is that if we have a simple radical expression, something that has the same nth root of 2 in both of these cases, we can treat this almost like a variable x, in that this is 5 square roots of 6 and this is 1 square root of 6. And whenever we have this situation where the radical portion of a addition problem exists where they're both the same, we can simply add them together. We can say 5 plus 1 is 6, so we have, in this given situation, 6 square roots of 6. And this applies to any addition subtraction situation of radical expressions. However, if we have a square root and we have the square root of x and the square root of y, nothing can be done to simplify this because the radical portion of these expressions are not the same. So this only applies to when the index is the same and the value in the radical sign is the same. The radicand is the same. So with that said, you might encounter examples like this, where we have the cube root of 54 and the cube root of 16. And the situations that might occur here is that we might not be able to add them directly right now, but maybe we can whittle them down into variations where that is possible. So for example, if I look at 54, the cube root of 54 doesn't give me a whole number, but if I do split and prime factor this out and say 2 times 27, and then 3 and 9, and then 3 and 3, I can see that a 3 would get pulled out and there would be a 2 left over. So then my next question is, can I do the same thing here? If I pull out a 2 and an 8, and then a 2 and a 4, and then a 2 and a 2, what I can see is that I would pull 3 3s out here and pull it up front, and I would pull 3 2s out here and pull it up front, and then there would be a 2 here and a 2 here left in the radical sign as a radicand. So if we go and we simplify this out a little bit, what we'll see is that we have the cube root of 2 times 3 cubed, and then we can try to add that to the cube root of 2 times 2 cubed. And actually, let's put these in parentheses to separate any distinction or confusion here. And what that allows me to do is pull these values out front, and then what I will get as a result is the cube root, or 3 cube roots of 2 plus 2 cube roots of 2. And what I want to point out here is that I have the same radicand with the same index. So what we can do is we can add these components together and say that we have 5 cube roots of 2 as our answer. And the same thing can apply in this situation. So I'm going to just prime factorize this again. And what I'm looking for is I'm just saying, all right, what are all my primes? I need to pull out 4 2s. Pull that out front. I can do the same thing with 48. Let's do 2 and 24. Let's go 2 and 12. 2, 6, 2 and 3. Again, I can pull out 4 2s. And we can pull this out front. And when we simplify this out, we'll see that 2 quartic root of 2 is present here, plus 2 quartic root of 3 is here. And what we would have to do at this given situation is you would want to simplify it at least, but one thing I want to point out here is that this is all the further we can go in this particular example. There's no adding or subtracting that we can do because the radicand is not shared. Sorry, this is to the fourth. The radicand is not shared. The indexes are, but the radicands are not, and we can't add them together. So that's all the further we could go, and that's an example of something that can't be added or subtracted. So with that said, I want to look at an example where we would multiply radical binomials. So we've talked a little bit about multiplying radical exponents before, and one of the things that I want to point out is that whenever we multiply radical binomials, usually we have it in this real to irrational format, real first, irrational part second, and then when we're going through and multiplying these, we just treat it as any other binomial. We just FOIL it, right? So we go first, so we get 2. Insides, we get plus the square root of 7. We go outsides, which would give us plus 6 square roots of 7. And last, which will give us 3 square roots of 7 times the square root of 7, which would equal 3 times the square root of 7 times the square root of 7. So then if we combine these two components, we would get 2 plus 7 square roots of 7. Okay, 1 square root of 7 plus 6 square roots of 7 plus 3 times 7 times 7, or square root of 7 times square root of 7 is 7, which would equal 21. So 21 plus 2 would be 23 plus 7 square roots of 7. And that's how you would FOIL out a radical binomial. Now, I'm just showing this to you so you can see some of the mathematical operations that you can do with radical binomials. Now, one of the really useful applications of radical binomials is if you multiply a radical binomial by its conjugate. So just like what we talked about in the previous section, is that if you have the exact same binomial, and what I mean by conjugates is that you just switch the signs, some really useful things happen, all right? And what I want to show you here is that when you multiply these conjugates, and you get 16 first, insides, negative 8 square roots of 3, outsides, plus 8 square roots of 3, and last, which would be negative 2 times 2 times the square root of 3 times the square root of 3. And one of the things that will always occur if you multiply radical binomial conjugates together is that the middle part will always cancel out. And then if we multiply these together, you'll get 3. Negative 2 times 2 is equal to negative 4. You'll get 16 minus 12. And then you'll get a final answer of 4. And you'll always have the situation where when you multiply radical binomial conjugates together, you always get a physical rational number as a result with no irrational components. So it's a really useful technique that we can use to our advantage. And where this comes into play and is really useful is when we are looking at rationalizing binomial radical denominators. So what I have here in this given situation is I have a value here that is a rational binomial radical. And like we talked about in the previous video, is mathematicians kind of have this thing about irrational numbers being in the denominator. We don't like it. So before we talked about, hey, if you multiply the correct number of parts of the same thing to it to get it so it cancels out, it's all good. But now we have this along with this binomial component that makes it a little bit more difficult to deal with. But one of the things that I've been trying to lead you up to is that if you actually multiply this denominator by its conjugate, then the denominator will become a whole number. So whenever you see this situation and you want to deal with rationalizing this denominator, what you do is you multiply the binomial radical denominator by its conjugate. And one of the things I want to point out in this given example is they actually put it in backwards. So what you have to flip is the sign of the radical part. So what we're going to do is we're going to go -3 square roots of 3 minus 2. Otherwise, it won't do what it's supposed to do. Just like we've talked about previously, we're looking at flipping the sign of the radical portion so that they cancel out when you FOIL them together. So if we do this to this particular circumstance and we put this on the bottom, remember when we're rationalizing the denominator, kind of the trick here is to multiply the whole thing by a factor of 1. So we're not changing it, we're just creatively multiplying by a conjugate in order to simplify that denominator, to rationalize that denominator. So what I want to do is I actually want to go and I want to try to solve this thing out and get it to do what I need it to do here. So in this particular instance, what I'm going to do is that I'm going to multiply this out. So what I'm going to do is that on the bottom, I'm multiplying these conjugates out. So what I'm going to do is I'm going to go first here. So I'll get -9 times the square root of 3 squared, which will just give me -27. And then we do insides. This will give us +6 square roots of 3. We'll do outsides, which will give me -6 square roots of 3. And then we'll do last, which will give us +4. So it's a little bit backwards from what we normally do. But then, again, kind of the idea here is this part cancels. We get -27 plus 4. And we get -23 as our denominator. Okay, so what we just did is we rationalized the binomial radical here. And so we get -23 in the denominator, and then on top what we're going to get is we're going to get negative square roots of 3 over 3 here, times that by 4. That'll give us -12 square roots of 3 minus 8. Okay, and now as we're going through this, what I want to point out is that if there's anything we can simplify out, we should. But in this particular instance, I don't see anything that we could do. So this actually is a simplified radical for this given problem. And we just solved this specific problem. We could multiply everything by -1, I suppose, and put everything positive in terms of signs. But we don't necessarily need to worry about that in this given instance. So something to just kind of keep in mind. So with this example, I hope that you feel like you have a better understanding of how to rationalize binomial radical denominators and how to add and subtract radical expressions. And with that said, let's do some math.